Modern AI agents are our digital proxies. They navigate the internet, retrieve information, and bring it back to assist with tasks on your local machine. We build these tools on a comforting assumption. The internet is essentially a vast library. It is filled with passive text and images, just waiting to be read. The risk emerges when the agent interprets fetched text as commands rather than data. If a web page contains hidden instructions, it can attempt to hijack the agent's programming, a process called prompt injection. For years, this remained an academic debate among security researchers, and that distance led many developers to treat the open web as safe. That debate ended in August 2026. A developer was using an AI agent to research a wiki about deleted video game content, and they tripped a wire. The site served the agent a hidden web page. It ordered the agent to permanently wipe out every file in the user's directory. The recursive instructions commanded it to move through all folders, specifically targeting the version control history so nothing could be recovered. The person who caught this meticulously documented the event. They hashed every artifact, timestamped it through an independent authority, and had servers verify it byte for byte. Researchers now have a documented, cryptographically verified record of a website serving code intended to destroy the user's local work. The target site was the Cutting Room Floor, a long-running, legitimate wiki dedicated to cataloging retro and unused video game content. The site was actively fighting off a real denial-of-service attack. To protect its bandwidth, administrators set up a standard block page, a polite 403 forbidden, designed to turn away normal human browsers. But the captured data revealed a forensic anomaly. The server's response changed based on who was knocking. Regular browsers hit the brick wall of the block page. If the request carried specific AI identifiers, the server returned a 200 OK status, bypassing the block and routing agents directly into the destructive payload. A standard block keeps everyone out. Rerouting specific bots into a separate room suggests a payload engineered to hunt machines. Once inside, the agent received a specific chain of commands. It was a clobber and unlink sequence, a technical set of steps designed to replace the user's entire working directory with a single empty file. Embedded right next to those instructions was a picture of the laughing dog from Nintendo's Duck Hunt, covered in text assigning moral guilt to the reader. The page was built to mock whoever found it. The commands never ran. The AI agent fetched the page, recognized it as a set of hostile orders rather than a wiki article, and refused to execute them. It warned the developer that the domain was serving destructive instructions and went back to its task. Every file survived. The model treated external content as untrusted data. While the defense held in this instance, relying on an agent's internal guardrails is a precarious security strategy. Server caching headers show this weaponized payload sat live on a highly trafficked research site for roughly 2 weeks before anyone documented it. Security researchers still classify prompt injection as an unsolved risk. The current defenses are effective, but they are not absolute. Relying on the AI model to always catch the trap means a single model update or a clever rephrasing could lead to a system failure. If the security of a hard drive depends entirely on an AI's judgment, the architecture remains vulnerable. The durable solution relies on established security controls. First, limit permissions so it cannot delete files. Second, isolate it in a disposable sandbox. Third, require human approval for irreversible actions. The model's internal refusal is a thin outer perimeter, the most fragile part of the stack. Content fetched from the internet must be treated as hostile by default. The agent's refusal is the last wall of defense, but the user is responsible for building the other three.